Hey everybody, today let's learn about one of my favorite things. I have a lot of favorite things in graphics, I think. Phong lighting. Phong is the name of the guy that pioneered it and published it. It's a pretty exciting thing. So, Phong lighting is a model of shading a surface that takes into account some properties of how light works. This is from 1975, so it's not exactly new. It's even older than I am. Phong lighting has three components. One, it has ambient light. Okay, ambient light is just a general light in a room, always the same. Okay, it doesn't vary with light, doesn't vary with direction, it's just always the same. It's just flat. It's how we've been talking about shading so far. You give something a color, it stays the color. But it also has something called diffuse light. Now, diffuse light it's based on the angle to the light. It changes as it moves away from the light. Based. If I look at my mouse, you can kind of see it's all one color, but it doesn't look like one color, does it? You can tell there's a light over that way, and it's shining on, and the diffuse is the general, not the shiny part in the middle, we'll come back, where am I? Not the shiny part, but the general fall off, like an orange is a really good way to show it. That's the diffuse lighting. My shirt has a lot of diffuse lighting. It's based on the angle to the light, and as I turn, it changes a bit. That's diffuse lighting. And we have specular lighting, or spectacular lighting. It uses the angle to the viewer, to the screen. So you can see a specular on here. As I move this, the specular changes to pointing at the camera because it's actually, where's the specular? There it is. I click somewhere. Things to work. It's actually the light coming in and bouncing off and going straight into your camera. So when that reflection angle lines up just right with the camera, or if you pick up something with your eye, when that angle lines up just right, that's called a specular. We add these three things together, and we have Phong shading. Let's look at the slide 22. So that's what Phong shading is. Not working. All right, there we go. So we have the ambient light, just like I said, it's flat across the whole object. We have diffuse light where it falls off. The light's obviously over that way somewhere, and it falls off. We have these speculars, the shiny bits that reflect back and poke you in the eye. You add them all together, and you get this nice diffuse plus ambient plus specular effect. That's Phong lighting, okay? How does it work? Let's learn it. Awesome. Woohoo. I like Phong. So it comes back to, you guessed it, vectors and math. So let's say we have a surface here. Okay? I'm going to define a few quantities. One, we have a surface normal. We've already talked about that. That's straight up from the surface. Okay? Two, we need to have a light somewhere in our scene. Okay? That's our light, it's the sun. We're going to call this, I'll draw a vector there. This is called L, that's my light vector. We also need something else in the scene. We need V, which actually I'll write this a little differently. We have U, this is your eyeball, okay, with your nice big lashes like there. Okay, that's U, and that's a vector to your viewer, that's V. There's one more quantity I want to put in here, and that's R. The R is the reflection across the normal. I'm going to put theta in there, the same as this one. R is the reflection of the light, because like I said, if the reflection of the light hits your eyeball, you get those speculars. Cool. So first of all, how do we do ambient light? Ambient light is the easiest. It just doesn't use our model. at all. Doesn't use that. Cool. Ambient light's easy. We just add the amount in. You've been doing that already. Put 0.3 blue in. That's your ambient light. I should probably label this. This is my surface. And you can imagine having triangles here, right? Okay. So that ambient's the easy part. Okay, let's see. Yes. First, I want to explain some notation. X hat. This is my normalized X. So if I put a hat over a vector, it means it's normalized. It means I convert it to length 1. And we talked about how to do that. And you'll see in a moment, I'll explain why it's so important to have that normalized. And of course, this friggin' computer, man. OneNote keeps pausing up. All right, let's see how much I can get going from memory. So diffuse light. So that's ambient, great. Diffuse light, as I said, diffuse, you use the angle to the light. It doesn't count the user, it's the angle to the light that matters. So we take the vector to the light, and we dot product that with the normal to the surface, okay? And we multiply it by m to get our result. M is some material color. We'll come back to that, right? So if you had a blue thing, it would just be like 1, 0, 0, right? Done. So all the red goes away and all the green goes away, and you're left with blue. But let's talk a little bit about what just happened here with this dot product. What on earth does this mean? Well, first of all, let's highlight that look and N are both length 1 because they're normalized, right? Now, if you go back and look at your dot product notes, you'll remember that if I dot product two vectors, it's the length of one times the length of the other times the cosine. These are both length 1. So this is just the cosine of the angle between them. We're back to our cosines. So what does it mean? Why do we care about the cosine of this light and the normal? Well, let's draw out our cosine again. Let's highlight a few regions. Right here, this is negative. It means they're facing in the opposite direction. Don't bother. And actually, you should never get this anyway, because we've already cut our back-facing faces, right? If they're back-facing, we don't have them. Or if the light's behind, I guess if the light's behind the object, we might get it. So if it's negative, don't bother. They're pointing away from each other. Forget it. The light doesn't help. If they're pointing exactly the same, if they're collinear, then they're the brightest. You multiply your light by 1, which makes perfect sense. If you're directly where the object is directly facing the light, bam! If your normal's right there, that's the brightest spot. And then as you move away from that and you're pointing away from the light, you're getting less direct light. You're getting more of an incident light. So this is what this cosine does. As the angle between my surface and the light changes, I'm getting more and more incident light until I hit 90 degrees and I have no light at all, which is the 0 here. No light. So diffuse uses the dot product between the light and your surface normal. If they line up, it's the maximum and it falls off at a cosine. That's it. That's all that we do for diffuse. Now specular, well, specular is not so easy. Not so hard, but it's not as easy as diffused. Now remember what I said about specular. Speculars happen when the light reflects exactly and shines in your eye. So we want to watch for this case here when the reflection and the view vector, when they meet. When these are really close, it's bright, right? And when they're really far away, it's not bright. So what we do for the specular is actually very, very similar. We take, let's get rid of the red. Let's go back to black. We take the reflection vector and we dot product it with our view vector. So we dot product the specular with our view. So if it shines right in our eye, this gives us a cosine, right? Because this gives us a cosine because they're normalized. Same thing. When they line up, it's the maximum brightness. When they're 90 degrees apart, no brightness at all. So if that light comes in, strikes your object, bounces, and hits your eye. Ouch! Exactly, right? That's when we get the maximum specular. So this is how we calculate specular light. There's one more piece to the equation. You do this, and then you take it to an exponent s. S is shininess. Shininess? I don't know how to spell shininess. S is shininess. I don't think it's a Y. Shininess? Well, you know what? If I write it messy enough, nobody knows I didn't spell it right. Shininess. I have a better idea. S is how shiny. There we go. And what the intuition here is, the exponent, it compresses the region, okay? So small s, no compression. We have a big region where the specular shows. If we have a large s, then we have a smaller region. So as s gets bigger, that shrinks. So that's it. We know how to do ambient. We just use a color. Diffuse, we do one dot product. Specular, we do a different dot product, and we calculate, we do the exponent to the s. The only thing I didn't really mention is, only thing I didn't really mention here, come on, is this. How do I calculate that reflection vector? Well, you can look it up. It's in your linear algebra book. You use the normal, and you can reflect across the normal. It's not worth my time to show you. It's pretty standard linear algebra, or you can look up Phong and find it online. It's not a big deal. So now to put it all together, the light at the point in your surface is ambient light, and you multiply that by MA, where all that MA is material ambience. How much your material reflects ambient light. So what you do is you set this to be a vector of 0 to 1. Right? So if I have a blue surface, I just set the blue to 0.2 and I'll get a bit of blue ambient light. Right? If I want to keep white, I use them all the same. If I put this to be 1, I get 100% ambient light. It'll be solid white. So this is how much ambient light to mix in. And then I add in material diffuse plus my diffuse calculation. Again, this is the same thing. It's just a vector, 0 to 1, each one. Basically, how much percent of the diffuse should I take? Put it as 0.5, and you're half brightness of diffuse. And then plus material, material specular times my specular calculation. Cool. Same thing. That's it. So that's how Phong works. So you use this math, a few dot products, and you can get all those cool results that we showed on the slides. All right. So I'm going to stop the video. I'm actually going to do one more, and we'll come back and we'll finish up with shading. Thanks.